Imagine for a moment that you could hold all of time in the palm of your hand. Not just your lifetime, not just the lifetime of the United States, not even the entire history of human civilization stretching back 10,000 years. No, I'm talking about holding the vast, the unimaginably vast 13.8 billion year saga of the universe itself. Think about it. From the searing, impossible heat of the Big Bang to the formation of the very first stars switching on in the darkness, from the birth of our sun in a cloud of gas and dust to the moment you blinked right now and started watching this video. It's an epic story, the greatest story ever told. But here's the thing about stories. Every single one, no matter how grand, no matter how beautiful, has an ending. We are so used to looking back, so comfortable tracing our cosmic origins. We build giant telescopes to peer into the past. We study ancient light that's been traveling for billions of years just to reach us. But what if, just for the next 20 minutes, we do something different? What if we stop asking, where did we come from, and start asking the most profound, the most terrifying, and the most awe-inspiring question of all? How will it end? Really think about that question for a second. Let it sink in. The universe, with its 100 billion galaxies, each one containing 100 billion stars, the grand cosmic canvas upon which all of reality, all of human history, all of your memories, every love story, every triumph, every heartbreak has been painted, will one day be gone. The stars will go out, the light will fade, and all that we are, all that we have ever known, will become just a faint memory, drifting in the cold, dark, silent void. This isn't science fiction, ladies and gentlemen. This isn't the latest Hollywood blockbuster. This is the ultimate prediction of modern physics. This is what happens when you take the laws of thermodynamics, Einstein's theory of relativity, quantum mechanics, and you run the clock forward, not just millions of years, not just billions, but trillions, quadrillions, to numbers so large they break your brain. And here's the part that will keep you up at night. The way it ends, the how, the actual mechanism of cosmic destruction depends on a battle, an invisible war happening right now, all around you, between two ghostly forces. On one side, gravity, the great uniter, the force that holds your feet to the ground, that keeps Earth swinging around the sun, that binds entire galaxies together in a delicate cosmic dance. Gravity has been fighting for 13.8 billion years to pull everything back together. And on the other side, dark energy, the invisible, mysterious, repulsive force that is pushing the universe apart, tearing it apart, making galaxies fly away from each other faster and faster. This battle, this cosmic tug-of-war between the pull of gravity and the push of dark energy, will decide the ultimate fate of literally everything that exists. And today, right now, we are going on a journey to the end of time itself. We will explore the three leading scientific theories for the apocalypse of everything. Some of them are cold, some of them are violent, and one of them might be happening all over again, right now, in ways you cannot possibly imagine. So sit back, take a deep breath, because we're about to witness the death of reality.
To understand the end, you first have to understand the forces at play. For most of human history, For 99.99% of the time humans have walked this earth, we thought the universe was static, unchanging, eternal. The stars were fixed lights in a perfect celestial sphere. The cosmos was like a beautiful painting that had always been there and always would be. Then came Edwin Hubble. A man with a telescope and a restless mind looked at distant galaxies and noticed something absolutely impossible, something that would shatter our view of reality forever. He saw that these galaxies, every single one of them, was moving away from us. And not just moving, the farther away they were, the faster they were receding. It was as if the entire universe was expanding. Think about that discovery. Imagine the vertigo. Imagine realizing that the ground beneath your feet isn't solid, but the entire cosmos, all of space itself, is stretching like a rubber band. For decades after Hubble's discovery, cosmologists debated the fate of this expansion. Two ideas dominated, two possible endings. The first idea was beautiful in its simplicity. Gravity, the great uniter, the force that never sleeps, would eventually win. The expansion would slow down, stop, and then reverse. The universe, all those billions of galaxies, would fall back together, collapsing in on itself in a final fiery catastrophe. They called it the Big Crunch. The second idea was lonelier. In this scenario, the expansion would simply continue forever, gradually slowing down, but never quite stopping. The universe would grow cold and dark and dilute, eventually reaching a state of maximum exhaustion, maximum entropy. They called it the heat death. For a while, these were the only two options on the table, two possible endings, two different fates. And we just needed to answer one simple question to find out which one was correct. Is the universe heavy enough for gravity to win, or is it light enough to expand forever? It was the 1990s. Two teams of astronomers, rivals really, set out to answer this question once and for all. They were going to measure the rate at which the universe's expansion was slowing down. They studied something beautiful, exploding stars called Type 1a supernovae. These are a special kind of cosmic explosion, the death scream of a white dwarf star. And here's what makes them perfect. They always, always shine with about the same intrinsic brightness. It's like having a standard light bulb, 100 watt, placed at different distances across the universe. By measuring how bright they appear from Earth, you can calculate exactly how far away they are. And by measuring how much their light has been stretched, how redshifted it is, you can calculate how fast they're moving away from us. Simple, right? They were looking for deceleration. They expected to see that the expansion was slowing down. That's what every model predicted. That's what made sense. But when the data came in, when they crunched the numbers, checked and double-checked, they found something that made their jaws drop. The supernovae were dimmer than they should have been, much dimmer. They were farther away than they should have been. The universe wasn't slowing down, it was speeding up. Let me say that again. The expansion of the universe, the great outward rush of galaxies that began with the Big Bang, is not slowing down due to gravity. It is accelerating. It is being pushed. It was as if you threw a ball in the air, and instead of slowing down, instead of reaching an apex and falling back to Earth, it just shot off into space, faster and faster and faster. This discovery, this single impossible finding, rocked the world of physics. It won its leaders the Nobel Prize, and it meant one thing. Our understanding of the universe was fundamentally, catastrophically incomplete. There had to be something else, something we couldn't see, something we couldn't touch, something we couldn't detect with any instrument ever built. Some kind of mysterious, invisible, repulsive force pushing the universe apart, counteracting gravity on the largest scales. We call it dark energy. And let me tell you what we know about it, which is almost nothing. We know it makes up about 70% of the total energy budget of the universe. Everything we can see, every star, every planet, every galaxy, every human being, all the normal matter in existence accounts for less than 5%. Dark matter, another invisible substance, makes up about 25%. But dark energy dominates. It is the single most powerful force in the cosmos. We know it behaves like a kind of anti-gravity, pushing space apart. And we know, from our best measurements, that it appears to be constant, unchanging, a permanent property of empty space itself. But here's the terrifying part. We don't know for sure. We don't know if dark energy is truly constant. We don't know if it might be changing over time. We don't know if it's a new field or a modification of gravity or something else entirely. And that uncertainty, that cosmic question mark, is the key to unlocking the ultimate fate of everything. The destiny of the cosmos is a three-part story, and the ending depends entirely on the nature of this ghostly force. So let's look at the three possible endings. Let's look at how the universe will die.
Our first scenario, I have to warn you, is the most violent, the most dramatic, and frankly, the most terrifying. We call it the Big Rip. In this ending, dark energy is not just a constant, gentle push, it's something much more sinister. Physicists call it phantom energy. Imagine a force that doesn't just push galaxies apart, but its strength, its power, increases over time. It grows and grows, becoming more powerful with every passing moment, with every second, every millisecond, every infinitesimal fraction of time. If this is the nature of dark energy, if it really is phantom energy, then the fate of the universe is sealed. And it will happen on a very specific and, from a cosmic perspective, terrifyingly fast timeline. Let's fast forward. Right now, today, dark energy is pushing galaxy clusters apart. But our local group, the small cluster of galaxies that includes the Milky Way and our neighbor Andromeda, is still bound together by gravity. We're safe, for now. But in a Big Rip scenario, that safety won't last. As the force of dark energy grows, as it becomes more powerful, it will eventually overcome the gravity holding our local group together. The Milky Way and Andromeda, which are currently on a slow collision course, will be torn apart from each other. Their gravitational bond, forged over billions of years, will snap like a rubber band stretched too far. We will become an island universe, completely alone, drifting in an ocean of expanding nothingness. But it gets worse. Much worse. The repulsive force continues to grow. It's getting stronger now. Soon it will overcome the gravity holding the Milky Way galaxy itself together. The delicate spiral arms, those beautiful swirls of stars and gas that have graced our night sky for eons, will unravel. Stars that have been born together, lived together, orbited together for billions of years will be ripped from each other's embrace, flung out into the void like sparks from a cosmic fire. Our solar system, our sun and its family of planets will become a rogue system,
drifting without a galactic home through the growing darkness. But the force, the phantom energy, is still growing. It's accelerating now, and it's about to get personal. Soon, it will start to overcome the gravity that holds our solar system together. The sun, the anchor of our existence, the source of all light and life on Earth, will lose its grip. Its gravitational pull, which has held planets in stable orbits for 4.5 billion years, will be overwhelmed. Earth, our home, the only place we've ever known, will be cut loose, sent tumbling into the cold, dark space between the stars, no longer bound to the sun, no longer warmed by its fire, just adrift. But remember, the force is still getting stronger. It hasn't stopped. It hasn't even slowed down. Now it will start to rip apart planets themselves. Imagine standing on the surface of the Earth in these final moments. The ground beneath your feet, the solid rock, the mountains, the oceans, everything held together by electromagnetic forces, by the bonds between atoms, begins to feel the strain. You would feel a tugging, a stretching, first barely perceptible, then stronger. The ground would crack, the sky would warp, and then the Earth, our beautiful blue marble, would be torn apart into a cloud of rubble. Boulders the size of continents, then rocks the size of houses, then pebbles, then dust. And in the final, most terrifying moments, the phantom energy becomes so strong, so unimaginably powerful, that it overcomes the forces holding atoms themselves together. Yes, atoms. The electrons that have orbited atomic nuclei for all of time will be ripped away. The protons and neutrons inside those nuclei, held together by the strongest force in the universe, the nuclear strong force, will be torn apart. In the last fraction of a second, in the final nanosecond of existence, space itself will expand so violently, so catastrophically, that every single particle, every quark, every photon, every shred of matter and energy will be separated from every other. The universe will end, not with a bang, but with the instantaneous, unimaginably violent dissolution of all matter, all space, all time. The Big Rip is the ultimate cosmic nightmare. It takes everything you know, everything you love, everything that has ever existed, and rips it apart at the most fundamental level. If dark energy is phantom energy, if it's growing stronger with time, then we are living on borrowed time. The clock is ticking, and the end, when it comes, will be absolute.
Now, let you catch your breath. Let's step back from that terrifying cliff and look at a second scenario. A scenario that is, in some ways, more hopeful, more nostalgic. This is the Big Crunch. Remember our original debate, the one from before we discovered dark energy? For the Big Crunch to happen, the nature of dark energy would have to change dramatically. What if dark energy isn't permanent? What if, instead of pushing forever, it eventually runs out of steam? What if it weakens over time, or even reverses its effect? What if, after billions of years of cosmic acceleration, gravity finally gets the last laugh? In this scenario, the accelerating expansion we see today, the thing that won the Nobel Prize, is just a phase, a temporary blip in the life of the cosmos. Eventually, the push of dark energy will fade, and the pull of gravity, patient, relentless, eternal gravity, will begin to dominate once more.
The universe will stop expanding. And then, incredibly, impossibly, it will begin to contract. At first, the contraction will be slow, almost imperceptible. Galaxies that have been moving apart for billions of years, that have been receding from each other since before Earth existed, will begin to slow, stop, and then fall back towards each other. The great outward rush becomes a great inward fall. The light from distant quasars, once redshifted by the expansion, stretched to longer wavelengths, will begin to be blue-shifted, compressed, squeezed. As the universe collapses, light waves get shorter, more energetic. The cosmic microwave background radiation, the faint afterglow of the Big Bang that bathes the entire universe in microwave light, will shift, first to infrared, then to visible light, then to ultraviolet, then to X-rays, then to gamma rays. As the sky, which has been dark for so long, will begin to glow, faintly at first, then brighter and brighter, until the entire heavens are blazing with light. As the universe shrinks, things heat up, the temperature climbs. Galaxy clusters containing thousands of galaxies each will merge in catastrophic collisions. Superclusters, the largest structures in the universe, will crash together. Stars, once separated by vast distances, will begin to collide. The universe will revert to a hot, dense plasma, just as it was in its infancy, in the first moments after the Big Bang. But this time, the heat is coming from the future. As the temperature climbs into the millions, then billions of degrees, planets and stars will be vaporized. Atoms, which require cool conditions to exist, will be torn apart. The universe becomes a sea of searing hot particles and radiation, a cosmic soup of pure energy. And then, in the final moments, the entire cosmos, all the matter and energy that has ever existed, will be crushed into an infinitely hot, infinitely dense point, a mathematical singularity. This is the Big Crunch, the opposite of the Big Bang. The universe ends as it began, as a single, unimaginably tiny point containing everything. But here's where it gets really interesting. And I mean really interesting. What if that point, that infinitely dense singularity, isn't the end? What if it's a beginning? Think about it. In our own world, in nature, we see cycles everywhere. Day follows night, summer follows winter, birth follows death. The universe loves cycles. Some physicists, inspired by this pattern, propose that the Big Crunch isn't a stopping point, it's a turning point, a cosmic spring. Imagine a spring being compressed. You push down on it, storing all that energy, all that potential. You push harder and harder until the spring is coiled as tight as it can possibly be. And then, at the very moment of maximum compression, it springs back out. In this model, our Big Bang, the event that created all the matter and energy we see around us, was simply the bounce from the previous universe's Big Crunch. And our Big Crunch, if it happens, will be the springboard for the next universe. Time becomes a cosmic loop, an infinite cycle of death and rebirth. Universes are born, live their billions of years, die in fire, and are reborn again for eternity. This is the Big Bounce. It's a beautiful idea, a poetic idea. It gives the end of the universe a sense of purpose, of continuity. The death of our cosmos is not an ending, but a transition, a passage, the closing of one chapter so another can begin. But, and this is a big but, for it to be true, we have to be wrong about dark energy. We have to hope that its push is temporary, that it will eventually fade, that gravity will ultimately triumph. Right now, the evidence says otherwise. But the universe, as we've learned, has a way of surprising us.
Which brings us to our third scenario, the one that, based on all our best evidence, all our most precise measurements, is currently the most likely. This is the scenario that keeps physicists awake at night. Not because it's violent, not because it's dramatic, but because of its sheer emptiness. This is the heat death, also known as the Big Freeze. To understand heat death, we have to talk about something called entropy. And I promise, this will change how you see everything. Entropy is often described as disorder, but in physics it's more specific, more profound. Entropy is a measure of how evenly energy is spread out. Think about a hot cup of coffee. When you first pour it, the heat is concentrated in the liquid. The coffee is hot, the room is cool. That's low entropy. The energy is concentrated. It can do work. But what happens? The coffee cools down. It spreads its heat to the room. The coffee molecules bump into air molecules, transferring energy. Eventually, the coffee and the room reach the same temperature. They're in equilibrium. Now the energy is still there, but it's spread out evenly. You can't do any work with it. You can't run an engine. You can't make anything happen. This is maximum entropy. Now here's the mind-blowing part. The universe is like that cup of coffee. It started in a state of impossibly low entropy after the Big Bang. All the energy in existence, all the matter, all the potential was concentrated in a single, infinitely hot, infinitely dense point. For 13.8 billion years, the universe has been spreading that energy out, increasing the total entropy of the cosmos. Every star that shines, every supernova that explodes, every living thing that breathes is part of this great unwinding. In a heat death scenario, dark energy is what physicists call a cosmological constant. It is a permanent, unchanging property of space itself. It will push the universe apart forever at an ever-accelerating rate. This leads to a slow, inexorable, and agonizingly lonely end. Let's walk through the timeline. And I need you to understand the numbers we're about to deal with are so vast, they exist in a realm beyond human comprehension. It starts with the end of starlight. We live in what astronomers call the stelliferous era, the age of stars. For billions of years, stars have been lighting up the universe, turning hydrogen into helium, helium into carbon, carbon into iron, releasing energy that warms planets and makes life possible. But stars, like everything else, are not eternal. They are fusion engines, and they will eventually run out of fuel. In about 5 billion years, our own sun will run out of hydrogen. It will swell into a red giant, engulfing Mercury and Venus, possibly Earth. Then it will shed its outer layers, leaving behind a small, dense corpse called a white dwarf, a stellar ember, slowly cooling, fading into darkness. But the sun is relatively short-lived. The smallest stars, the red dwarfs, burn their fuel so slowly, so carefully, that they can shine for trillions of years. Trillions! For context, the entire history of life on Earth, from the first single-celled organisms to you watching this video, is about 4 billion years. A red dwarf star will outlast that by a factor of 1,000. But eventually, even they will run out. In tens of trillions of years, the last, faintest red dwarf stars will finally exhaust their hydrogen and flicker out.
the universe will go dark. No more starlight, no more galaxies glowing in the night, just darkness. But the story, the long, slow decline is just beginning. After the last star dies, the universe will be filled with the corpses of stars, white dwarfs, neutron stars, and black holes. These cold, dead objects will continue to drift apart, the space between them growing exponentially due to dark energy. Galaxies will dissolve. The structures that took billions of years to form will be stretched into nothingness. And here's where it gets truly strange. Over incomprehensible timescales, even these dead objects, these ultimate remnants of stellar existence, will not be safe. Through a bizarre quantum process predicted by Stephen Hawking, black holes themselves will slowly, gradually evaporate. Hawking radiation, as it's called, is a quantum effect at the edge of a black hole's event horizon. Particle-antiparticle pairs are created. One falls in, the other escapes, and over time this steals energy from the black hole. It slowly, agonizingly slowly leaks away. A black hole with the mass of our sun would take, are you sitting down? Approximately 10,000 billion billion years to evaporate. That number is so large, it's meaningless. It's a timescale so far beyond human experience that comparing it to the current age of the universe is like comparing the lifespan of a mayfly, which lives for just one day, to the entire history of planet Earth. For a supermassive black hole, the kind that sits at the center of galaxies, it could take even longer. Numbers so vast they have no name, no point of reference, no way for the human mind to grasp. But eventually, inevitably, after all those eons, the last black hole will pop out of existence in a final flash of radiation. And then, what's left? The universe will consist of nothing but subatomic particles. Electrons, positrons, neutrinos, photons, all of them drifting alone, isolated in an unimaginably vast, cold, and dark space, separated by distances larger than our current observable universe. And they will just drift forever. The universe will have reached maximum entropy. Every photon will be the same temperature. Every particle will be isolated from every other. There will be no more energy gradients, no more work to be done, no more change, no more stars being born, no more galaxies colliding, no more life, no more thought, no more anything. Time, in a practical sense, will become meaningless. There is nothing left to mark its passage. No events, no changes, just an eternal, frozen, silent void. And then, what's left? This is the heat death. Not an explosion, not a collapse, but a long, slow, gentle fade to black. The universe simply runs out of energy to do anything interesting ever again.
So, which is it? A violent rip that tears atoms apart? A cyclical bounce that births new universes? Or a slow, cold, eternal freeze? The honest answer, the only honest answer a scientist can give you, is that we don't know yet. And that uncertainty, that cosmic question mark hanging over our existence, is what makes this field of science so incredibly exciting. All three endings hinge on the true identity of dark energy. Is it the cosmological constant that Einstein once called his biggest blunder? A simple, unchanging property of space? Is it a new, dynamic field, one that could change over time, growing stronger or weaker as the universe ages? Or, and this is the really radical idea, is it a sign that our theory of gravity itself, Einstein's general relativity, the foundation of modern cosmology, is incomplete on the grandest scales? Right now, as you're watching this video, there are space telescopes scanning the sky, collecting data, trying to answer this question. The European Space Agency's Euclid telescope, launched just a few years ago, is mapping the distribution of galaxies across cosmic time, looking for subtle clues about how dark energy has behaved. NASA's Nancy Grace Roman Space Telescope, set to launch soon, will do the same thing with even greater precision. These missions, these incredible feats of human ingenuity, might rule out one of our scenarios, maybe two. They might tell us, for the first time in human history, how our story really ends. Think about that for a moment. We are living in a golden age of discovery. We are the first generation of humans in all history capable of not just asking how the universe will end, but of gathering the actual data to answer it. The same curiosity that drives a child to look up at the night sky and ask, why, is driving us to build billion-dollar space telescopes to discover the fate of all reality. We are tiny beings on a pale blue dot orbiting an ordinary star in an average galaxy among billions, and we have the audacity, the sheer magnificent audacity, to try and read the last page of the cosmic story. That is beautiful. So, how will the universe end? Will it scream to a halt in a big rip, torn apart by an ever-strengthening phantom force? Will it collapse in a big crunch, only to bounce back in a new big bang, an infinite cycle of death and rebirth? Or will it simply fall asleep, drifting into a heat death, a big freeze, where the last black hole evaporates, the last particle decays, and nothing, absolutely nothing, ever happens again? Maybe it ends with a whimper. Maybe it ends with a bang. Or maybe, just maybe, our universe is just one page in an infinite book, and its ending is simply the beginning of a story we cannot yet comprehend. Whatever the answer, one thing is absolutely certain. It won't happen tomorrow. It won't happen for billions and trillions and quadrillions of years. The night sky, with all its stars and galaxies and cosmic wonders, will shine on for a time far longer than the entire history of life on Earth. We have time. But this knowledge, this understanding of the eventual fate of everything, gives us something precious. It gives us perspective. It reminds us that our time, our brief moment in the sun, our planet, our civilization, our very existence is a brief, fleeting, beautiful, precious anomaly. We are a brief flicker of warmth and light in a universe that is slowly, inexorably heading towards a cold, dark, and eternal night. The end is coming. It's inevitable, but not for a very, very long time. So before the last star goes out, before the final galaxy dissolves into darkness, before the last black hole evaporates into nothingness, we have a chance to learn, to grow, to explore, to love, to create, to ask questions, to marvel at the beauty of existence. We have a chance to look up at the night sky, filled with its countless stars, its infinite possibilities, and wonder, what comes next?